About now, you are probably asking yourself why we are doing these things. The math seems really excessive. So far, it's just been equations. You haven't even had numbers. It's just been letters. It's just a little bit more excessive than anything we had last quarter. Well, for one, all of these things are building up to harder stuff. So the reason we're doing all these things with little point charges is because we're about to take the next step and look at continuous charge distributions, of which there are many in real life. Second, there's very important concepts hidden in all of this math. Deriving things really can help you get a deeper understanding of the concepts if you're paying attention to what the steps are for the derivation and you're being reflective about your results. In addition to that, and all of physics, learning stuff makes your brain stronger. The more you push your brain, the stronger it becomes. Physics is the sit-ups of the brain. With that in mind, let's extend all this stuff with point charges and look at a continuous charge distribution. Let's say you've got not 3 plus charges in a line like before, but now we've got a whole rod of charge. Let's look at a finite line of charge. So you've got a total charge Q. So you've got a total charge Q distributed over a rod of length L. I want to know, what is the electric field over here, some distance x away from the center of the rod? We don't know what the electric field is for a rod of charge yet. We've got to derive that. Right now, all we know is the electric field for a point charge. So let's pretend this rod is just a whole bunch of little tiny point charges. For example, there's this little point charge that has a charge dq. You know, because when you do calculus stuff, when you take like an infinitesimal something, you put a d in front of it. So instead of the whole q, it's dq. So this dq at the position of our dot is going to make electric field that points this way. Since there's a symmetric situation here, there's going to be some dq on the opposite side of the rod that's going to make electric field that points this way. And since those are equal distance from our point x, these are going to be equal in magnitude. You can see from this picture that, like, pairwise, all of these electric fields are going to cancel in their y components, and overall we're just going to have one electric field that points to the right. So now we just have to figure out what that's going to be. We only know the electric field of a point charge. Those little dq's, those are like little point charges, and each one contributes a tiny bit of electric field, dE. The little bit of electric field is k dq over r squared, and r squared in this case, so if that's r is equal to x squared plus however far down that little chunk of charge is, y squared. If this is the center of the rod, then this little bit dq is some distance y away from the center of the rod. We only want the part of this electric field that points in the x direction, because looking at our picture, all the y components are going to cancel. That means if you've got this electric field pointed at some angle theta, you just want the cosine component of that. That theta I drew is the same as this theta. So to get the x component, we want to multiply that by a cosine of theta. And cosine of theta in this case is x over r, or x over that square root of x squared plus y squared. Okay, so the little contribution that a bit of charge makes in the x direction is k times dq over r squared, and r squared is x squared plus y squared. See, the r is squared, so I took out that square root thing. And then times the cosine of theta. So if I expand that out, there's x squared plus y squared under both parts of that, so I can group that together to get an x squared plus y squared to the 3/2. So this is the component of the electric field that a little chunk of charge makes in the x direction. Now all we have to do is integrate over that whole entire line of charge. The problem is that this integral has a dq, and you can kind of guess, looking at this picture, that dq is not what we really want to integrate over. That electric field is going to change based on that distance y that all the charges are away from the center of the bar. So we really want this to be an integral with respect to y. One thing we do know about dq, since the rod is uniformly charged, q over L is equal to a constant, and that q over L should be the same as dq over some dy. So that infinitesimal amount of charge over that infinitesimal amount of space that it takes up on the rod, dy, that ratio should be the same as q over L. This is the magic part. When you do these integrals, this particular step is kind of tricky. Since it's a uniformly charged rod, we can make this substitution for dq. So dq is q over L dy. So going back to that equation, it's k times x times dq, which is q over L times dy over x squared plus y squared to the 3/2. Now we got something we can integrate. We just need to integrate this to get the whole electric field. So on the right, we're going to integrate from negative L over 2 to positive L over 2, because you remember our bar has a length L and it's centered on the origin. I don't know about you, but I do not know this integral off the top of my head. This is definitely an integral table occasion. I went ahead and looked this up for you. The integral of dy over x squared plus y squared to the 3/2 is y over x squared times the square root of x squared plus y squared. Boom, there you got it. We're totally going to have a similar type of problem on the next exam, and I will give you an integral table. You don't have to bring your own, but you will need an integral table. Plugging that in, we get that the electric field is going to be kqx over L times y divided by x squared times square root of x squared plus y squared. Just want to point out, since all of our charge is in the y direction, that's why we're integrating over y. We're integrating over the charge distribution. X is a constant here. You're at some position x and it's not changing. We do need to evaluate this, and we can simplify a little bit, like we can get rid of that x and one of those. And we need to evaluate this with our integration limits. You can check my work if you want through the miracle of video. It comes out to k times q divided by x times the square root of x squared plus L over 2 squared. And this is in the positive x direction. Ta-da! This is the electric field along a perpendicular line for a finite line of charge. How do we know if this is right? You will especially want to know that when this comes up on a test. So first we should look at units. The electric field for a point charge is kq over r squared. And in our electric field equation, we've got a k and a q on top. And if you look on the bottom, we have a distance times another distance, like x squared plus L over 2 squared square rooted has units of distance. So we're good on units. We should check limits. If you're really, really far away from this rod, if x is way, way bigger than L, that implies, that's the symbol for implies, that x squared plus L over 2 squared is really just squiggly equals x squared. So if you were to put in x squared where that stuff is, you get square root of x squared, that's just x, and then times the other x on the bottom, it's going to be kq over x squared. That means if you're really far away from this finite line of charge, it's just going to look like a little point charge that has a charge of q. All right, let's try it with numbers. What's the electric field strength 1.5 centimeters from the middle of an 8 centimeter long glass rod uniformly charged to 15 nanocoulombs? Do this and enter it on Canvas.